And we are live also in YouTube. Okay, you can start.
So I start speaking?
Yes.
Okay. So it is a great pleasure to have as a speaker of this colloquium Ferdinand Schmidt-Kaler, a leading figure in the realization of quantum computers within the €1 billion project of the European community named Quantum Flagship, launched to push the research of innovative quantum technologies. Schmidt-Kaler got his PhD in München, and after a research position in Garching in Paris in the group of the Nobel laureate Haroche, and in Innsbruck, he became full professor in Ulm, and now he's in Mainz as leader of the initiative Quantum Bit. He is a member of the ERC evaluation panel and chair of the Quantum Optics and Photonic Division of the German Physical Society. His research interests include laser cooling and trapping of atoms and ions and quantum information technologies, as reflected by the topic of this colloquium, with the title, Modern Quantum Technology with Trapped Ions. In the technological context, the so-called first quantum revolution resulted in amazing inventions, such as the laser and the transistor, at the basis of the present semiconductor-based computers. This revolution was dealing with macroscopic systems, basically, and it was mainly related to the peculiar properties of the spectrum of the energy and the loss of individuality of identical particles in the quantum world. Instead, the present second quantum revolution deals with quantum properties of single quantum objects, such as atoms, which we are now able to manipulate. It is mainly related to the superposition principle that allows a system that have at the same time potentially two properties that in our classical world are mutually exclusive. Let me just mention the famous dead and alive of the Schrödinger cat. And the property of entanglement that allows the reality of two components of a composite quantum system to be deeply connected without physical interactions, none of the two components having an independent reality. The second revolution has originated one of the fastest growing areas with whose possible technological applications include quantum communication, quantum simulation, and quantum computers. In fact, the use of the two above properties allows a quantum computer to deal in a sense simultaneously with classical independent computations, thus reliably performing, for some problems at least, a task better than a classical computer, a result which is sometimes called quantum supremacy or quantum advantage. Let me make a remark of local interest. The technology of trapped ions described in this colloquium is the focus of our department proposal to the call for establishing a world-class research infrastructure at the University of Padua to bring a quantum computer also here. And finally, let me give an announcement for the attendees of the webinar. If you have urgent questions during the colloquium, please click on the icon Q&A in English and DER in Italiano on your screen and put your question there. Further questions with the same modality will be collected at the end of the colloquium. And now let's Schmidt-Kaler to introduce us in the fascinating universe of quantum computing. Please.
Well, thank you very much for this wonderful introduction, and you covered a lot of the topics which I will now describe in more detail. Thank you very much for the invitation. I'm very pleased that I can talk, and I hope that when we come into the year 2021 with maybe better Corona conditions, that I can really visit you in person and discuss a lot of things. I think we have a lot of things in common interest, and there is the quantum world is becoming closer, and we are also collaborating with Simone, for example, Simone Montangero from your university. So there is a lot of common things. One should really establish this collaboration and go on. But now coming to my talk. I will talk about modern quantum technology with trapped ions, and mainly I focus on quantum computing. So I give you some motivations why a quantum computer could be useful. But first of all, I have to tell you how a quantum computer works with its bits and pieces. And this is qubits and the gates, which are the basics of an ion-trapped quantum computer or any quantum computer. There are different architectures, like in normal computer systems, you have also different architectures. And I tell you how one can build an architecture which is scalable, also towards a large number of qubits. And the second really urgent thing is that we need to be more reliable over long term. In our experiments in the lab, we can work with a PhD student, aligns the lasers and so on. But if we are really building a machine that is industry compatible and can be used for everybody, then we need industry standard qubit devices with about 100 qubits at least. And how to address this topic, that is now current research. And at the end, I will maybe have some time to talk about a different way to build a quantum computer. So what you see here is now in the bottom. I hope you can see my mouse. I will put this, wait a moment, this spotlight here. So you can see here individual trapped ions. So these are calcium ions trapped in a Paul trap. And these are the main player in my work. Okay, next. Okay, if we go into the history, we see that computing information processing is really an old field. The first computers have been mechanical. There have been wheels which turn around, like Leibniz invented a first computer, and then the other mechanical computer was based on relays by Konrad Zuse. Actually, these mechanical devices have the problem that they sometimes work and sometimes don't work because the mechanical things are really a little bit shaky and they don't work all the time. So people were extremely happy to use electronics. And there are two ways electronics can kick in. Either the electronics is happening in a semiconductor, like a transistor, and the transistor was invented by Lilienfeld in 1929 in Berlin. And then it was growing into a processor like the Intel 8080, which features about a couple of thousand gates. And that is really a good computer. And the older of us have even used an Intel 8080 processor in their early computers. So this is the way how it went in the semiconductors. And of course, it comes together with the miniaturization of the electronics. The vacuum electronics is another option. We know the electrons can also move in free space in vacuum and can switch currents. And those which love music have maybe an amplifier which is based on these vacuum tubes. Very nice sound. So these are different options to do quantum computing. And you see it to use classical computing, and this evolved quite a lot. Digital information processing is now extremely powerful. That is because these computers are using many CPUs in parallel, millions of CPUs in parallel, and because these computers can have extremely high gate rates, okay? They consume a lot of electrical power, and the first question is, are there really no limits? There are limits, and these limits are typically indicated by the Moore's laws. There are many Moore laws. For example, one Moore law is that versus the time that we see, the most powerful computer increase, like on this logarithmic scale, they increase without limit in their performance, that make more and more petaflops per second. And so it is astonishing. Also, you can see that the amount of transistors on a CPU increases in this power law fashion as the one before. So Moore himself, he said this should stop at a time of 2005. When he did his prediction, he said, okay, at this time, this will flatten down because then we cannot do it any longer. But then when this time came, he made a new promise and he said, now it will flatten down in 2025. So, well, we don't know when it flattens down. But the problem is, if you want to make a computer that is twice as powerful as the older one, you have to make it twice as large. In the quantum computer business, it is different. You have just to add one single qubit to a computer. So a computer of 100 qubits is twice as powerful as a computer of 99 qubits. So that means this is really exploring the computation space in a totally different fashion. And if you want to double the power of a computer, you can just do it by adding one qubit, while in a classical setting, you have to make the whole structure twice, okay? The whole energy consumption twice, the whole infrastructure twice. So that is, of course, a big promise of quantum computing. I go into this in detail, but why is there limits to the classical computers? So if you look very much in detail what is happening in the transistor in these integrated circuits, then you find very, very small gates, very, very small transistors, which are only at this length scale of a few nanometer. And people have been building the so-called 14 nanometer technology, then the 7 nanometer technology, and nowadays they are discussing about 3 nanometer technology. At these scales, you have only a small volume of your silicon, which is only used for this transistor, and there are only a handful of doping atoms which are used for switching it. So you can already see the grains of the atoms, basically, if you look into the details of such a transistor. So we see this has an end, and the end is certainly there where we are facing the single atom size, and that is not so far away. And that is the reason why the Moore's law will stop to scale up at some level. So that's the reason the future is quantum. The future is quantum for two reasons. First of all, quantum is already at the level of single atoms, single photons, single ions, single quantum objects. And second, we use the quantum laws, the specific laws of quantumness, to enhance the computational power. So these are the two arguments. We can parallelize processes in a completely different way as in classical computing. So let me try to explain these technological steps at the example, which is completely well known to you. You use a handy, you use Wi-Fi all the time, but how does it come about? It started with a discovery with a theoretical guy named James Maxwell, and he had the bright ideas about the Maxwell equation. See the Maxwell equation here. And actually he found that these are coupled equations, and one of the solutions of this in vacuum is that you can transmit electromagnetic waves. So he predicted electromagnetic waves just on paper, just because of his bright ideas, just because of the theory. This was in 1864. And then experimentalists came, and that was Heinrich Hertz. And we know the Hertz, that is still the oscillation frequency of anything is measured in Hertz. And here you see the monument of Hertz in Karlsruhe, where he found really an experimental proof of that electromagnetic wave exists. So you see, you have an arc which is transmitted, an electromagnetic wave is transmitted through a lab, okay? This is, of course, completely useless. You can do it in a lab and you can be happy. You find the electromagnetic wave and you can put mirrors or prisms or blocks or whatever. You can study electromagnetic waves. but you don't use them. And it was only this gentleman here, Marconi, a son of rich parents. And if you're going from the Po flatness to Florence, you pass with a highway into the mountains, and you see on the right-hand side, you see an antenna, and left-hand side, you see also antennas. And this is the place where Marconi first studied electromagnetic waves, now on a much larger transmission distance. And he wanted to make them useful, okay? He didn't want to study them in lab. He wanted to bring them out of the lab and really make something out of it. And it was the British Army. They wanted to know that their army has a victory on the other side of the channel. And they want to send this message quickly to London back. So they were looking for transmission of signals over the distance and very fast. And now, of course, Maxwell tells us the speed of light is the transmission of these waves. So it is a fantastic way to transmit messages. And it was in 1897, so about 30 years later, then they were just proposed that Marconi could send a message, let it be so, over a large distance. And that was the onset of this fantastic development of electromagnetic waves, and we use them all the time since then. So you see, it goes in 3 steps. You have a theory invented by bright people. You have experimentalists which test this basis, and they really verify everything. And then you have the technology, which is based on all this, and try to make it useful. And exactly the same happens in quantum physics also. So here you have the early heroes of quantum mechanics. You can see Max Planck here at the side. You can see Niels Bohr, Heisenberg, Schrödinger, you see Pauli, you see Dirac, all the guys which are very famous, and they did Gedanken experiments with single atoms, single photons, and they understood the things like quantum superposition and entanglement. And then, well, they were very skeptical about what you could do really. So I have here the citation of Erwin Schrödinger, and I want to read it for you. It's fair to state that we are not experimenting with single particles any more than we can raise a very crazy animal that is already 100,000 years ago in the zoo. But we know it's not true. This is not true, and there is a more optimistic view by Richard Feynman. There is plenty room at the bottom. So there is plenty room, and never underestimate the fantasy of experimentalists that they can realize some ideas. So you see, this Ichthyosaurus is here, but we trap this in our lab. So we have the chance to do this, and we can tame this animal and raise it in our zoo. That is a Paul trap, which we use for this. So the good container for this trapped and fantastic animals in quantum physics, this is exactly a Paul trap. So Wolfgang Paul received the Nobel Prize in 1989 for the invention of the Paul trap. You apply to an electrode structure an alternating electric field, and this way you can trap a single ion or an assembly of ions in the center. And then it was Ted Hensch and was Arthur Shallow and others, and also Dave Wineland, and they invented optical cooling. So you send in the laser and you can cool this trapped ion or a trapped particle, trapped ion, to temperatures which are as cold as compared to our room temperature, as the sun is hot in the inside. So it is really orders of magnitude. We are reaching micro-Kelvin temperatures routinely. So this is a fantastic tool which we are using for our research. And I can give you an example. We have this trap potential. If you think of Laplace equation, you know that in a free space, you have always binding direction here along the x direction and an anti-binding direction. You cannot have a confining potential in all directions according to the Laplace equations. But if you make this prefactor time varying, then you can trap, and I want to show you here this. So you see, if you rotate subtle potential, then the ball is nicely trapped in the middle. Okay? And in the same way, we can trap single ions. Actually, we trap them for hours, for days, for weeks. They can be trapped even for months in our traps. They are very, very stable in the traps. And here are some examples from Innsbruck, where I worked a lot before, Oxford, Boulder in the States, Aarhus, and of course you have seen the trapped ions in our traps in Mainz at the very beginning of my talk. So these ions are oscillating because the potential is a harmonic oscillator potential. And you see this nice oscillation here in a real video, which we took by stroboscopically imaging the ions. So now you can do amazing things with these trapped particles. And this is now what was the main achievement of Serge Haroche and Dave Wineland. And they received the Nobel Prize for measuring and manipulating individual quantum systems. I think this is kind of parallel to what Heinrich Hertz has done. So proving there is really the chance to do this, that is proposed by theory. So producing a Schrödinger cat and really doing this in the lab and doing looking how to operate superpositions, how to operate entanglement and so on. And to measure this really in the lab to prove it experimentally. So they are kind of this second step where you say the theory is developed, now you're going to the experimental proofs. And this was in the last decades, I say. And then from that on, now we're starting the third step. The third step is to make it really useful for everybody, to make it useful modern technical application like a quantum computer. And here you see the inauguration ceremony in the Hofburg in Vienna, October 2018. And you see the deputies of the ministers here sitting of Europe. They all inaugurate the quantum flagship. So that is what we have now. And we are going to show what is the status. And here is a little bit a cartoon of the whole situation. The question is, how is your quantum computer prototype coming along? And the answer is the project exists in a superposition of being both totally successful and not even started. So that is exactly the truth. And I can tell you why this is true. It is totally successful in the experimental scale, and it not even started to be useful for other people to use it. So for external user, I would say it not even started to be useful. So far, what you can do on a quantum computer, typically you can do on a computing device that is very, very conventional. And Simone is, of course, a person who uses computers. Simone Montagera is using a lot these computers. He thinks about very clever tricks to use computer codes in order to simulate quantum systems, even to limits challenging the quantum simulator, so to say. So the farther he puts his techniques, the more we have to run against this wall and make our quantum simulators and quantum computers better and better to beat him finally. So that is really the point. At the moment, the usefulness is not yet there, but it will come. It will come as it comes in the case of the electromagnetic waves. It is a very complicated task, and now I will walk you through the things we have to take into care for this. So first of all, there are really very important goals in quantum computing. And as our chairman explained, the quantum computers can solve really problems much more efficiently than classical computers. But for this, you need a lot of qubits, like 1,000 qubits, and we are not there. We have also errors in the qubits, and this is leading to the problem that we have the noisy intermediate scale quantum ages. So that means our computers are not perfect enough to really do the job. But there are low-hanging fruits. We could do simulations, and I want to focus especially on quantum chemistry, because here you can really do a lot already with a limited amount of of qubits, and that will really lead to technology advances in the chemistry industry. Let us summarize what a quantum computer has to do. You have to have quantum superposition, which are alpha 0 plus beta 1. So we talk about the Bloch sphere, and on this Bloch sphere you can point in any direction, and the complex amplitudes alpha and beta, they control where the Bloch vector is pointing. So you can make a superposition of 0 plus 1, you can make a pure state 0 or 1, and you can do arbitrary quantum superpositions here. But you have to do it in a scalable system of many, many qubits. And then you want to initialize all the qubits, say, to the state 0. Then you are starting with single and 2-bit gates. So look to my hands. A single bit is just rotating a qubit in the Bloch sphere around its axis in different directions, okay? But a 2-qubit gate means if this qubit is pointing up, this one should be turned. If this pointing down, this one should be not turned. And this is kind of a controlled NOT operation. And this is a 2-bit gate. Then we have to take care. These are quantum superposition. They are entangled state at the end if we are using many, many qubits. And that means they are fragile. Like our chairman told us, the Schrödinger cat is not living very long if we have a very large one. And so the coherence times of single qubits and of quantum registers have been much, much longer than the gate operation time, the time we need to execute the algorithm. We have to measure the qubits at the end of the algorithm, and we have to connect also different parts of a quantum processor to make a network of computers. This is very important for scalability also. So this is a really demanding list, and I show you how to implement it with a trapped ion. So first of all, how do we manipulate these superpositions? We select our two eigenenergies of the level scheme. Here in this case, I take as an example the energies of a calcium ion. A single calcium ion has this S ground state, and there's a metastable D state, a long-lived D state, and now you can shine in laser light and excite from the ground state to the excited state, and you can stop the laser pulse at some instant and generate a superposition of 0 and 1. And in this way, you can generate arbitrary, by controlling the amplitude and the phase of the laser, you can control the arbitrary superposition of alpha 0 plus beta 1. And as this lifetime here of the D state is exceeding 1 second, you could be sure this is now living for more than a second that I get this superposition. So this is already a single bit gate. Now, how do we detect that this ion is in the superposition? Of course, if we want to measure, we will break the superposition. The moment of measurement that is typical for quantum processes, the moment of measurement projects into eigenstates. And that is exactly happening when we shine in here laser light on a short-lived transition. And then if the ion is scattering photons, we know it was projected to the 0 state. If it is just very dark, then it was in this state, it was projected into this state, into the qubit state 1. So you see here on the inset, you see that the brightness of the ion can be very, very different. In this case, it scatters a lot of photons per second. In this case, it scatters no photons. You see this in the case of 1, it goes to 0, the intensity. So you have a very, very good discrimination when you measure the qubits. So out of your ions, some of them will be just dark and the other ones will be bright. And this way you can measure the quantum state on a linear crystal of ions very easily and very, very effectively. Actually, you can exceed a fidelity, a threshold of 99.99. That means you are wrong in less than a per mil of the cases, yeah? Which is a very good fidelity. Now, I want to show you here from our lab our single bit rotations. So we send in the laser beams here to the ion, that's the green dot, and then we turn the Bloch vector from up, down, and it's like if you're doing piano, then you have to train your fingers and you try to do it very fast and very often. And then if you do this, then you can play some real music. So here you see the experimental result. This is looking like a simulation, but it's real experiments because it's so perfect. It looks like a simulation. Each of these points, very small, is 100 experiments where we apply a laser pulse for a certain time. And we increase the time along this axis. And you see the Bloch vectors going up and down and up and down and up and down many, many times. I hope you can see this. And this is how we do the single bit gates. And you see only after about 10,000 times, we are getting a little bit noisy, so to say. So that means you could do this gate really to a high quality. We can do at a level of a few 10 to the -5, we have errors which are only kicking at error per gate is only a couple of 10 to the -5 per gate. That means we do pretty perfect single bit gates, okay? So now the question is, how coherent is this state? Oh, I forgot to say, the single bit operation time is a couple of microseconds, okay? That's the time scale at which you can switch the qubit from 0 to 1 or to arbitrary superpositions. What is now the time scale? How long can we keep a superposition? So we generate a superposition at the moment 0, and then we look how long does it survive. This is the survival of the qubit. And you see this time which we can wait is now exceeding a couple of seconds. Actually, we see that the qubit survives 2 seconds. So this is 6 orders of magnitude longer that the survival of the qubit superposition is as compared to produce this qubit in the superposition. So this is a wonderful separation of timescales, which is the basis of all this success, you know? Now we have to come to the 2-qubit operations, and they are more complicated. Here you see the photos of Peter Zoller and Ignacio Cirac. They are the heroes to find the first proposal for trapped ions to do a 2-bit operation, as I sketched with my hands. When the first ion, here's the truth table of this qubit operation. When the first ion is in logic state 0, the second ion, which we call the target qubit, should not be turned, okay? So that means 0, 0 makes 0, 0. And also when the first ion is in 0, the second should not be turned. Also from 1, it stays 1. Only if the control bit is 1, then the target should flip from 0 to 1 or from 1 to 0. So it looks extremely simple. You have trapped ions here, okay? You have a row of trapped ions. And this is how a theoretician thinks a Paul trap looks like. And here are the common modes of vibration indicated, and you address these qubits by lasers. And then, depending on what is the spin state of this control bit, the target bit should flip or not. That is exactly what we want. And it took from the proposal of Peter Zoller and Ignacio Cirac, which was in 1994, it took a couple of years until in Innsbruck we could realize it. And at the beginning, not with a very good fidelity, but later on with better fidelities. And nowadays, you use this common mode of vibration, which I showed here in this film, for gates which are much better than 99%. So it basically fails only in some per mil cases. That means you can do thousands of gates, literally, before you are completely done. Of course, we know a computer should do thousands of gates, and so we have to improve on this because it's still not good enough. So here is the principle. You have your spin number. This is coupled to the common motion of ions in the harmonic potential. You see, if this is oscillating, the other one is also oscillating because it's a Coulomb spring between these two ions. And now this oscillation is used to control the spin of the second ion. So it's a spin coupling, but it is mediated. That means it can act over long distance. You don't need to put these ions very close to each other because it's not a direct spin-spin interaction. which would work only on a length scale of a few nanometer. But this is mediated via the motional degrees of freedom, and that makes it so nice and long range. Okay, now I'm talking about trapped ion quantum processor architectures. Here you see a photo of our trap, which we used all the time. Now it's replaced by a better one, but I still love it because it was our first trap where we could do a lot of in this museum. So what do we want from an architecture, from a quantum architecture? We want to have it scalable. And scalable means we want to have a high number of qubits. If you read the newspapers, this is only the only number they spell out, but it's wrong. If you have 100 qubits and they are not good, it is not helpful. So you need to have a fidelity of gate operations that you really can, okay? And if you can only entangle neighbors and not entangle the next neighbors, for example, then it is also not very helpful. And that is measured by the qubit connectivity. So all this together gives you the so-called quantum volume. It's important because it's a universal measure of how a quantum computer is working. So if you have 10 qubits and they're all connected, it may be much more helpful instead of having a situation where you have 100 qubits and only next neighbors are connected. So what we get from the press is a very limited amount of information. And of course, the big companies like Google and IBM, they want to make records. And this is just in the sheer number of qubits. It is really meaningless, okay? But this is only the first step on a quantum computer architecture. The next step is that we have to take care of the qubit preparation and readout fidelity, because we need this. We need this for quantum error correction. We need also in-loop qubit readout. We need, during the operation run, to shuttle one qubit into a safe region and measure it. And depending on the outcome, you can do a decision on this further run of the algorithm. That means a real-time feedback on the quantum algorithm. And this is important for quantum error correction. And only then you can go into mathematical qubits and go out of these noisy intermediate scale quantum processors. And last not least, as our chairman told us, quantum computers are not good for everything. Quantum computers are very, very specialized tools. And the best is you connect them to a high performance computer. So if you have a high performance computer and connect a quantum coprocessor to it, you have basically the best of all worlds. This is called hybrid computing. And that is what is relevant for making chemistry simulations and so on. So this is your wish list, okay? And now I'm coming to the two architectures which are commonly used with trapped ions. And you see here now the leading figures of this field, Rainer Blatt, Christian Roos, Tommy Mons, and Chris Monroe in the States. So I was a part of this group, and I like this very much because here you see the ions trapped in a nice linear trap, and they are one linear crystal. Now, if you want to address with a single bit operation ion number 5, then you send a laser beam to only ion number 5 and do the corresponding gate operation that you want to do. So you use focused laser beams. You see this also here in the sketch. You use focused laser beams to address single ions. And this is only possible because single laser beams can be focused to about a micrometer, and the distances between the ions are more than a micrometer, like typically 3 or 4 micrometers. So you can address one ion without too much cross-talk to the other neighbors. And never underestimate the ability to address ions with a laser. Actually, if you compare to other technology, it is so beautiful. You have a wire, a light wire, which goes to a qubit. And if you don't use it, you switch the laser off. Imagine you have a solid state qubit which has an electric feed. You cannot take the wire away. The wire is always in your way. When you want to address another qubit, you have always all the wires there, even if you don't use them. So they that just pick up a lot of noise, and there are just a lot of mess around. Here you have your qubits basically only sitting in vacuum, and the wires to these qubits are only laser beams, which you can completely switch off, and they can go through each other. They don't take space, so to say. So this is the linear ion crystal individual addressing scheme. But at some moment, if you put 100 of ions here, then these ions come closer and closer, and then the ability to address single ones is going to be worse and worse. And that means you have to go to another step to get scalability. I forgot to say there are companies by Chris Monroe and by Rainer Blatt and company here, IonQ and Alpine Technologies, and they are already doing a commercial step, so kind of Marconi-like, and going the next step. So the other architecture which I want to show you is the divided et impera architecture. This is the old Romans idea, how they, Germans, they would divide the tribes into different sections, and then they kill one after the other. That is the way how we kill the problems. We kill every problem only one after the other. And this is the wonderful idea of Dave Wineland here, who came up with a so-called quantum CCD. So you see, you have a more complex trap where you can shuttle the ions around and move them to different sections. So you have one section where you have laser beams and do the gates, and you have memory section where you just save qubits at the site. Laser pulses generate entangled states, and the microsegmented trap allows to position the qubits and move the right bit, like in your classic computer. You don't use all the bits in your processor. You have a hard disk, okay? And there you save all the information which you don't need at the moment. And that is exactly the idea of Dave Wineland. So you only use those qubits in the processor, central processor region, which are operated. Okay, and Honeywell is a company going this direction. Now we are also in Mainz following this direction, and we have these nice traps where we can move the ions around. I don't go into fabrication details. There's an electronics. If you have 100 of electrodes, you have also to have 100 of very, very low noise and very fast analog channels to control the motion of the ions. And we can do this, and you see a lot of papers. I don't go into these details. We can basically shuttle ions around. We can move ions to different places. We can rotate crystals and change the order. We can move a single ion very quickly. And what you see here, this takes only a couple of microseconds, and it happens without a lot of energy in the modes. So even we do all this, what I call quantum register reconfiguration operations, even we do this, we can still operate quantum gates with very good fidelity. And that's a major achievement you can read in these papers if you like. So we have basically followed this Dave Wineland architecture. And for this, you have to develop a lot of technology because it's like a gearbox. You have your high-level commands in the quantum information processing language. That is basically the algorithm you want to execute. But then what should you do? Which qubit should be where? What kind of laser pulse should be applied to what qubit to execute it really, okay? So it's like a chess playing. You have your figures on the chess, and you don't know initially, if you're not a good chess player, how to move them around that they have the maximum active force against the enemy here to execute the operation. So these are the sequence commands, and these sequence commands calculate ion position. Then the trap has to be applied with these corresponding voltages with the ramps. And then this is the output that delivers the right voltage to the right segment of the ion trap and moves the ion to the right place at the right moment and delivers the laser pulse at the right moment. So this is all very complicated, and we are still struggling with this because it's kind of as an assembler code for our quantum processor, which we have to write. And typically in your computer, you never deal with some problems, what bit is at what kind of level in the stack or so. That is really the complication we have now. But let me go to some example. The scalable production of a 4-ion Greenberger Horn-Seilinger state. So a maximally entangled state, you see, this is the state we want to produce. This is exactly as our chairman said, this state has a global perfect, we perfectly know the state, but if you look to a single entity, it is randomly either 0 or 1. Okay, so this is really where individual properties lose the mean, have no meaning any longer. This is a large entangled state. And how do we do it? This is the time. These are all our 4 qubits and they're initialized in the state 0. Now we apply a Hadamard gate, which makes exactly a coherent superposition of 0 and 1 for the first qubit here. And now we use this qubit as a control bit for the second qubit. It means we bring now a second qubit to the first qubit, we move it in, we apply the laser pulse, and then we don't need the first qubit any longer. We can shuttle it to the side. But we need a third qubit, and then we bring the third qubit to the second one. We do again the laser pulse for entanglement, and then we need a fourth qubit, but we don't need the second one any longer. So we move this to the side. Yeah, so that's how it is generated. And at the end, we measure whether the outcome of this of the algorithm is really this state, the Greenberger Horn-Seilinger state. And here you see what we do. The time is now going down here, and these are all the segments of our trap. And you see the ions, these are small little balls here, A, B, C, D. We need these 4 ions. First, we cool them in the central region, then we move them away. And at some moment here, we do a gate operation here between the green and the blue. And then we don't need the green any longer. We move it to the side. We need a red, a blue and the black one, and so on. So we move always these ions into the place which are necessary. And that's the whole algorithm, which is composed out of 324 segments to segments moves and 8 separations and 12 gates, 3 2-bit gates. And all this works, we can produce the target state with about 95% fidelity. That means it fails only in 5% of the cases. And this is the proof of this entanglement, because you see the off-diagonal elements and the diagonal elements. That means you really see a coherent superposition of everyone is in 0 plus everyone is in 1. Okay? So this is a scalable production of GH states. And now I go a step further. This is quantum error correction. And here we join the teams of Rainer Blatt, Jonathan Holm, and theory support, and working on quantum error correction. And I want to convey this message because it's very important. Quantum computers in the noisy intermediate scale, they have a big problem. They are analog computers. And everybody who has worked with analog computers has a problem with analog computers because these are complex amplitudes, alpha and beta. And imagine they are just wrong by a little tiny bit. So this Bloch vector is not exactly there, but it's a little bit wrong, okay? Just a little bit wrong, okay? And this is a very tiny little bit, so you cannot really see this. It's too small to see it. And the question now, if you do a lot of gates, then all these errors accumulate, and then you have a problem because the outcome is wrong. How can you digitize analog quantum errors? That's the question. And error correction does it. So you entangle your qubit with an ancillar system. So now you have this common quantum state. You have the qubit in the situation with no error, and the ancillar has no error, and the qubit has a full error, and the ancillar shows a full error. But as long as you don't measure the ancillar, it is still in a superposition of these 2 options, okay? But now you measure the ancillar. You measure the ancillar, and what happens? If the ancilla shows green light, it tells you there was no error, and the ancilla shows green light and there is no error. So it projected onto the subspace where there's no error. So this was a wonderful way to correct an error, by the way. You just measured the error away by measuring the ancilla in the green state. The other option is also good. If the ancilla shows red light, then you know for sure there is a full error, and then you know exactly what you have to do, because you really apply only the inverse operation to the error. And this way you can make digital errors out of the analog errors that the quantum computer typically has. So in reality, you have to do it in a topological quantum error correction way. And you need 7 data qubits to encode 1 mathematical qubit. You see the overhead is pretty large. And on top of this, you need 2 ancilla ions to measure what is the outcome. So the syndrome is measured by another 2 ions. So altogether, you need 9 ions to implement 1 error-free or error-less corrected qubit, mathematical qubit. How do? You measure the parity of this red plaquette. And say if you measure the parity is okay here, then you don't know whether the error is here or here or here. There is no error, okay, on these red qubits. Now let's say you measure now the blue plaquette and there is an error. What you know already is that number 2 and 3 are not wrong because you measured the red plaquette before and that was okay. So you have not detected where the error is, but you are, because if you measure a quantum system, you would project the state. So you have to take care that you don't do this during the error correction. And that means you need to know there is an error, but you have to preserve the quantum superpositions. And that is if you measure the stabilizer outcome of the blue packet, now you find an error. It can be either qubit number 5 or 6. And if you measure the green plaquette and you find also an error, then you know it was the number 6, and now you can correct the qubit number 6 for exactly this error. So that is topological quantum correction, and it's a pretty complicated algorithm. You know, there are only on the red plaquette already 4 data qubits plus 2 ancilla. In reality, we need 9 qubits. But we do this now for 4 data qubits only. And you see the algorithm again. This is the time going down. Here you see the 6 qubits. We have to shuttle them around to the right positions, do the gates accordingly, and so on. And you see this is a pretty long algorithm. At the end of 90 configurations and 150 transports, we find this. If we have the state 1, 1, 1, 1, 4 times 1, this is an even state. The syndrome shows bright. You see there is a little bit of light here. Yeah? And that is good because it should show bright. There's no error. But if one of the data qubits is 0, 1, 1, 1, 0, the syndrome should be dark. Oh, you see it is not totally dark. It should be really dark. So we see we can do something which approximately does the right job, but not to the sufficient fidelity at the moment. So we have to improve on our algorithm and our methods and our gate fidelities, that we really make this totally bright and this totally dark. And then we can use this readout of the syndrome to correct the data here. Okay. So that's exactly what we are doing at the moment in the team headed by Rainer Blatt and company. Now I can wrap up a little bit about the key figures of quantum computing with trapped ions. The single readout fidelity is really very, very good. The gate fidelities are exceeding 10 to the minus 4 errors. So they are in the range of a few 10 to minus 5 errors only. The 2-bit gate fidelity is only a per mil, okay? Not so good. The gate operation times are typically 30 microseconds, but there are some examples where people can do it faster. Now, we can reconfigure registers, and this takes between 30 and 80 microseconds. But we can do it also very fast, but then we have to pay a price. The coherence times I showed you the 2-second coherence times, but we will expecting minutes, and it can be even improved further to many minutes. We are using these microsegmented traps, and we have a lot of segments. We are facing now problems where we have 130 segments, and then we can shuttle really big amount of ions back and forth, but it is like a complicated game. And these ions are trapped for days and maybe under good conditions even for weeks. So this is the status of trapped ions, quantum computing. Let me compare a little bit with our main competitor that are superconducting qubits. And here you have the example of the IBM quantum computer. And if you go into IBM quantum computers, then you see typically this connectivity schemes. So you see here, the qubit number 13 cannot control by anything, but it can control qubit number 12 and 1. And the qubit number 1 can control 0 and 2, but nothing else. So the connectivity between 1 and 7 is extremely bad. You cannot really control the 7 with the 1 qubit. This is very, very different as compared to ions, where you have an all-to-all connectivity. So of course, this makes a big difference in the quantum volume. The other point is what I want to make is you see all the wires going down here to the qubit section. So the more qubits you have, the more wires you have. I told you in our case, we address them with laser beams. Laser beams can go through each other and they are not intersecting in some way. So that is another advantage. But the IBM people are very good in programming. So they have a nice language to do your job on a quantum computer. You can put your Hadamard gates, and this is something which we have to do, and we have currently a BMBF project running where you would finally be able to access the Mainz quantum computer from outside as an external user and run your own quantum computing algorithm. So let's go to the other point, the Google computer. This is the architecture of the Google computer. This is a qubit in the middle of a cross, and there are qubit connectivities to all the neighbors. And the green symbols indicate the connectivity to, so one qubit is connected to all its 4 neighbors in this architecture. And what you can see is the error per gate on a single bit is about 0.1%, 0.16%. For the trapped ions, this error per gate was a few 10 to the minus 5. The 2-bit errors are comparable, while the ion trap has still some advantage here. And the readout here is 3% wrong or 4% wrong. We exceed 99.9%, 99.99% if we want. So what they do, however, and where they are very, very good is the gate speed. They can do the gates much, much faster as compared to the trapped ions. So they implemented a quantum algorithm like this. They entangle every qubit with its neighbor. So they do a gate over this junction A, then over B, then over C, and then over D. And then they do this for all the qubits all the time. They try to entangle, or they entangle in this way 53 qubits, which is a lot, and it's a really great achievement. They use 20 cycles here to do this, and now it is not a misprint. The fidelity of the outcome at the end is a few per mil, okay? It is not that we have 95% fidelity, as I showed you before, or 80 or 50 or so, but the outcome is mostly wrong, okay? And in some per mil of the cases, it is okay, it is right. So the fidelity is a few 10 to minus 3. That is obvious, because if you do these gates 20 times, then all the errors are accumulating, okay? And that means over many, many repetitions, because this device is so fast, you can still see this bit of quantum outcome. That is what happened in this quantum processor. So the advantage of a superconducting qubit is you can operate it very fast. You can operate it in an assembly which is built by cleanroom technologies, and it is in this way a very reliable technology. And here we are in our lab. Here you see our lab with a lot of mirrors and with a lot of posts, and everything is in the air and everything is vibrating a little bit, and you need PhD students to adjust all these mirrors all over the time. So that is a very, very painful thing. So we need to go this step towards an industry standard where everything is in racks and you're not really harmed by laser instabilities or vibrational frequencies or so. So really going to a scalable qubit device with industry standards. Here you see our steps. We use this micro-segmented trap here, which is fabricated by glass, etched glass, laser treated and then etched, and you see very nice edges and very nice shapes. And this is composed out of these chips. They have a large and optical versatile access on all directions. And now what is very specific, we have 2 addressing zones, or at the end, multiple addressing zones. So think of this piano player. Fortunately, a piano player has 2 hands, okay? He can do very fast motions with each hand. If you want to address another tone, he has to move the hand to another place, and there he can work again fast. So the same idea is here. You can, working with local addressing of laser beams, you can address all these qubits which are here in this laser addressing zone 2 very quickly, kind of with your right hand. You can at the same time operate in the addressing zone 1 with your left hand, also very quickly. But then you want to move your arm in order to play something different. And we do not move the arm. We move the keys of the board. We move the qubits that they are under the right. We bring in new qubits from the side and let them addressed by here the laser beams. So this is the reconfiguration of quantum registers which are prepared and then shuttled into the addressing zone. So in that sense, it's a merger, it's a joining of the both assets of these 2 architectures which I showed you at the beginning. The local addressing, which is very fast, but doesn't work for very large quantum registers, and the shuttling, the idea of Dave Wineland, which allows scalability. So, and that comes together with all the industry ready components, and you see the addressing zone, you see the electronics, which is modular. If you have just a trap with more modules, you can just sneak in more electronics, and then you can address even larger traps and even larger assemblies. The lasers are coming with fibers and are much more stable than before. And as I told you, we are connecting this quantum computer as a co-processor with a low latency to a high performance computer, which is situated in Mainz already. That's Mogon 2. And this is one of the fastest German computers that can be then interacting with the quantum computer back and forth. And you can use, by penny lane programming in the future, then program your own code and apply it on our system. That's the goal in 3 years, actually. So let me wrap up and come a bit again to a high level. So we've seen trapped ion qubits are pretty nice to operate, high fidelities, high qubit preparation fidelity, very, very long coherence time. The superconducting qubits have the asset that they are nicely fabricated in solid state technology. They have extremely high speed in detection and in gates, and this is a clear asset. There are also neutral atoms like Gutenberg atoms, and so they can interact, and their I think the highest number of qubits has been achieved. And the photonic devices can also be used for quantum computers. They are extremely fast. They are fast as light. And interconnectivity of nodes is easy. And finally, there are quantum dots or single donor systems. And they are wonderful because here you could connect to the common technology of solid state processor like silicon or so, where people really know how to make electronics. And you could make a quantum processor which is sitting just on top of a conventional electronics processor. That is, of course, a big asset. The problem of the whole business is that all these individual perfections here in coherence time, in gate speed, in number of qubits, in interconnectivity and fabrication status are not coming in one platform, but always on different platforms, okay? So that means the race is open. I don't know which one is going to make it. I think we will see quantum computers in a different way, which are specialized for different tasks, corresponding to the certain assets of the different approaches. And that is what we will see in future. And then at the end, maybe a merger of the assets of different approaches is possible. That is, of course, interesting to see. I don't know. I'm very interested to see this, but this is on a good way. And here you see a lot of companies which are investing in this and doing this already today. So I'm coming now to the end of my talk, and yeah, this is a little bit of wrap up, and you can read all about the quantum computer here, our papers on the homepage, which we have. Just go to quantenbit.de, and then you find all the papers and all the references. And I thank you very much for your attention, and now ready for your questions. Thank you very much. This is the wonderful team which made it only possible, and the funding of different sources, including the quantum flagship, which was highlighted by our chairman, and also German Science Foundation and Bundesministerium and European sources, whatever. Thank you very much.
Thank you very much for this very clear and complete overview of on the quantum computers. So if the attendees have some questions, please. You just write in the Q&A, or in Italian in the Q&A icon that you can find in your screen. I have actually maybe one question, which is maybe a little silly, but just to ask, because in theoreticians sometimes have the idea that they can use braiding and anions to construct a quantum computer. What is your feeling about? Is it something which is science fiction?
No, I think, well, it is of course a wonderful physics idea, but I feel it is not at the moment, it is not yet at the level of the other technologies which I showed here. So it could further be included here in this solid state technology maybe, but at the moment I think the leading technologies, the leading platforms are mentioned here. It is wonderful physics. It's a little bit more in the status 2 and not yet in status 3, I think. But the race is open. I said this. It is the quantum computer is not a sprint; it's a marathon. So it's like Tour de France, and we have not even finished the first day. That's my clear observation. So I don't know. People may come up with a very clever idea and then they make it work. But at the moment, the braiding has not really led to well, it is from the concepts, of course, I know there can be gates, there can be single bit operations, and the promise is that it would be error correcting from the beginning, so to say. But I think this is not based on experimental evidence so far.
Okay.
So in the moment you want to braid qubits there, you will have to address, you have to apply certain fields, and they are noisy, and then you will also introduce errors. So I think it's not okay to compare a theoretical construction, which is maybe fantastic, with the experimental status, and then you find out, of course, in the experiments, okay, but this was not exactly so easy as proposed. So that was my observation for trapped ions, actually.
Okay, so it's basically, you think it's a second step. Yeah,
it's in the second step, yes. It's not yet in the third one, yes.
Okay, thank you.
Roberto, I might have a question also, if
yes,
I can.
please.
Before, I would encourage, encourage also the students to make questions here. This is, Ferdinand is here for you, so take the chance to make your questions. But while they are thinking, Ferdinand, I would like to ask you, what is the highest challenge that you see in front of you in this wonderful plan that you have shown today to us? Or do you simply think it's something that, you need some time and you will get there in 3 years? So it's very...
Simone, it is, we are, I think the answer is very clear. We are facing only engineering problems. That is a little bit an unfortunate answer to a physicist like you, but the engineering problems are the hardest at the moment. So the typical problem is, how do we fabricate these chips in the right way? Everybody knows it should be a clean surface. It is not clean. So we need a better fabrication technique, a better cleaning technique. How do we focus laser beams to 1 micron? This is, of course, since AB is not a miracle any longer. So you know what you have to do, but then there are 10 laser beams on this side, 10 laser beams on this side. Each of them have to be on one focus, and they have to be adjusted to the spacing of the ions. So you need extremely stable alignment. You need extremely stable conditions from the laser frequencies as well. So we are demanding a lot from the experiment. And we need also a continuous operation if we want to go into a user facility. No experiment we are running is like this so far. From a car which you would build in your garage from some stuff, and you say, okay, I know how a car is you have 4 wheels and so on. Yeah, and you cannot sell it. You cannot, maybe it runs for 20 meters and then it explodes also. So it's really the engineering part which is the most important, and we need to have physicists which have this fable for engineering, and on the other hand they need to know everything about quantum physics. So we need quantum engineers in that sense, and these are people which we are bringing up now in the groups. And with this stimulus, that is the only way. It is always the people which are educated, and they have to be educated to make up to a quantum engineer. That's the point. I think that's really from the physics, there is basically everything is set. Of course, things can improve, but we are not limited by this at the moment.
Okay, I found some questions in the Q&A. So the first is the error correction protocol and Silicium qubits placing, connecting, etc. dependent or independent on the particular circuit under implementation?
Well, I go back to the transparency. So this is just to bring you the idea of how an analog error is converted into a digital error. Of course, you could not do this in a real setting, because if you measure the ancilla, then you would project the qubit into either 0 or 1, and that would completely kill the superposition information. So this is just to tell you how I can, by entangling with an ancilla system, measure an error and make the error from an analog to a digital error. But to do so, you have I can also say in a quantum bit, you have the upper state, the lower state, and all the phases. So you have complex amplitudes, alpha 0 plus beta 1. And that means you can do much more mistakes as compared to classical bit. So you can not only flip the qubit by error, but you can also dephase it. And the idea is always we have a majority vote. So one simple error code is you have 3 qubits, which are in the superposition up, plus down, down, down. And now you measure not the property of the qubit itself, whether it is up or down, but you only measure, are the qubits equal or not? You measure the first and the second and measure whether these are equal or not. If they're equal, it's nice. If they're not, you know one of them is wrong. Now you measure the second and the third, and you see again, one of them is wrong. You don't know which one is wrong. But if you find this first and the third is okay, then you know the middle one was the wrong one, because that's the only solution, okay? And then you can say, okay, this one did the error, now correct this one. And you can measure the parity, and this is the extension of the parity measurement, that is measuring the stabilizers of this 4-ion plaquette. This is kind of the extension to it. You measure whether they are equal or not equal. You don't measure the properties, okay? And that is the point how you can then determine if all these are equal under the stabilizer, then you know nothing is wrong. If there's something wrong, if one of them is wrong, then the stabilizer will show a minus sign, -1, and not a +1. And then the ancilla will show up, oh, there's an error on this plaquette. But you have no idea where the error is. Can be qubit 1, 2, 3, or 4. And that is necessary that you don't know it, because otherwise you project the quantum state. So this is always a very, very subtle way to get information, but not the information about the qubit itself. And this is very tricky indeed. And this is the minimum way to do it. And it depends, of course, on the code. You can have this 7 data qubit color code, which is the most efficient one. There is a 9 data qubit short code, which takes more gates and more qubits. So we prefer this one. And there's other codes which are protecting against more errors. So here, this code is only protecting against 1 error which happens. 1 out of these 7 qubits may do an error, and you can detect and cure it. But if there are 2 errors, then it's over. And then you need another code. And then you need another algorithm again. Yes. So I hope that was the question, the answer.
So I think it's in some sense, this error, the error correction protocol is in a sense almost universal. In a sense, you can apply it to many different circuit protocols.
Absolutely, absolutely. You can apply exactly the same circuit to a Rydberg quantum computer, Rydberg atom quantum computer, or to superconducting. This is absolutely right. Yeah.
Okay. So I have other questions. Is how many courses you think you have to teach to give the basics of quantum information and ion quantum computers? Each course of 40 hours.
Well, I think it is not so complicated at the end. You know, it is only about zeros and ones. So, but Simone, we shared courses together in Ulm, and I think there were 12 lectures, and we made a joint enterprise. Simone took care of the theory part. I took part of the experimental part, and it was a lot of pleasure, I think. So I would say in a semester you can get quite a good impression what quantum computing does. Yes.
Okay. And the other is more general. It says companies commercializing quantum technologies compete alongside academic groups for European and other funding. Do you think that this competition will rather benefit technology transfer and its research basis, or will it shift the focus completely away from the fundamental research? So it's a kind of very general.
It is a very, very interesting question. And I have to say, as I'm now in the quantum information business for about 30 years, I see that the atmosphere has changed quite a lot with these press releases by Google and IBM and these battles and so on, with a lot of money. And you have to compete now as a university group, and you can compete. That's my observation, because the students which we have in the lab, the PhD students, the master students, they are so brilliant, they can make it against engineers easily in these companies. So Honeywell, for example, and INQ, they have 50 people on board, and I think they are not much better than university groups at the time. Of course, on the long run, in a university institute, you cannot develop technology only. So this is really an ugly valley of death, yeah, where you have to hand over these things at some level to an industry partner, and you cannot do this as a research group to develop only technology. And as I told on the question of Simone, there is a lot of technology challenges, engineering challenges. My way out is, I have a couple of PhD students, very successful ones, and they started now in companies, or they start in companies. And this is the way you have to educate people, and they are going into the companies, or they are starting their own companies. For example, 3 of my former PhD students are working with Alpine Technology now in Innsbruck with Rainer Blatt and Tommy Mons. And of course, this is a constant exchange of ideas and technology. So at the moment, you have an asset from this development. And on the long run, I don't know. In superconducting qubits, I think it is a little bit disencouraging for research groups to compete with Google and IBM. In the atomic technologies like Rydberg and atoms and Rydberg atoms, or atoms and lattices or ions, the university groups are so strong that they can easily compete at the moment with the companies. Also photonics, there's also beautiful research. So in these platforms, there is still a lot of manpower in the university, but in the superconducting starts that it is a little bit disencouraging for the university groups, I guess. I don't know how this is going to end, but of course there's this gap. You know, I want to deliver a quantum computer that does something, but I need all this technology, and the question is, how can I get this? It costs a lot of money. And so I'm very grateful that finally Germany waked up. It took so long. And I'm very happy that the European flagship started, because that was the wake-up call for Germany. And if I have now can go back to this transparency where I show, oh, it is too slow, sorry. But here, the BMBF here, Bundesministerium für Bildung und Forschung, they have been hesitating for about 2 years whether they should be, they are responsible for applied research. So they are funding things which are then paving the way towards an industrial development. But they have been very, very cautious whether they should fund at all quantum hardware in Germany, whether it would make any sense to do quantum hardware funding. And it was only the telephone affair. You know about this telephone networks by Huawei and Cisco, and either you get a spy chip from the one company or a spy chip from the other company into your telephone transmission. And if Europe is not building on its own strength, then we will have always foreign hardware, and we don't know what is inside, see? And this is, of course, very dangerous if you have a quantum computer that can be operated only by companies or by states where you don't know what happens. and you want to calculate maybe a new chemical reaction, you have to open all your wisdom to an external company or to a foreign country. And that is, of course, a high risk. And this was triggering the BMBF to say, okay, no, we cannot really give up about the hardware. And that was, I'm very grateful to European Commission that it started the flagship, and that was a wake-up call for Germany, I think. So now this valley of death is a little bit covered by this funding, see?
So there is another question, some of clarifying, to clarify better, how are entangled the ions with the laser? I mean this.
Okay. Yes, I was very short on this. Sorry, but well, I can show it with my hands. So you have the common modes of vibration of an ion crystal. Okay. These ions are oscillating together. That means if you kick this one, the other one will be also moving. So there are common modes of vibration. And now you can make these motions spin dependent. I have now my fingers up or down or down, down or up, up. And depending on the state of the spins, you change the modes of vibration in frequency. So now you excite some modes, and you can only excite a certain mode if the spins have the right pointing up, okay? And this makes the interaction between two ions, because you excite the mode of two ions only if the spins are pointing up. If the spins are pointing down, this mode is not excited. And now you use this in phase space. You think of a classical spring. You have an eigenfrequency, and you push it a little bit off the resonance frequency. At the moment you start, the amplitude increases, and then you're getting out of phase, you're decelerating the oscillator again until you come to rest. And what you did is you excited the motion and you de-excited the motion. And at the end you say nothing happened. I'm again in the same state as before. That's not true. You got a geometric phase. That's a Berry phase, and this phase has to be adjusted by clever, proper choice of the laser tuning and the laser power, that this phase is exactly -1. That means if you do this excitation, you get a phase factor of -1. If you don't do it, you get a phase factor of +1. And that makes you a phase gate. So it is a spin-dependent force which you use on the common modes of vibration. That is basically what you do. And the common modes of vibration are coupling, because the Coulomb force is so super strong, coupling the ions at a distance of a few micrometers very strongly. And there are very, very few systems which are so strongly coupled as Coulomb systems. So Rydberg atoms can also do this, because there's huge dipolar moments, and then you can also couple at a distance. But all the other spin systems do not couple so strongly. You need to come very close together in order to couple them. And then, of course, you have the problem with addressability, because if the qubits are very close together, then how can you address them singly? So that's the asset of ions, this long-range interaction, which is made spin-dependent by driving it, spin-dependent with the laser. Yeah.
There is a question about the cross beam measurement, where you use one ion with two laser beam from orthogonal directions. Is it correct?
If you well, you have what you typically have. You have multiple excess of laser beams, and if you shine in two laser beams at the same time at different angles, then you get an interference pattern. And this standing wave is used to induce these spin-dependent forces. So if I have to go back so much, sorry. But it is, maybe I have it here. Yeah, well. So this is, for example, here we do a Raman transition. So we use a specific qubit, which is called the spin qubit, because we are using only the electron spin of a calcium in the 1s ground state. So the electron, the nucleus has no spin, calcium has no spin, calcium 40. And so if we are in the S state, there's also no angular momentum. So the only momentum is the spin of the electron. And the spin of the electron can either point along the magnetic field or in the other way around. This is our qubit. And so we are basically have the calcium ion only to trap better the single electron. And the single electron, which is hanging around the calcium nucleus, this is the qubit. And we flip the spin of the qubit by sending in laser beams at orthogonal polarization. So this is the polarization is pointing out of the plane, and here the polarization is in plane. And this drives the transition between an m equals -1 state, which is qubit 0, and m equals +1 1/2. That is m equals spin equal qubit equal 1. So our encoding is that the spin 1/2 system, either -1/2 or +1/2. This is 0, this is 1, okay? And then we drive a Raman transition, and the asset of this choice of qubit is that we are in the ground state. So the ground state cannot decay to anybody. So there is it already ground state. So the only decoherence mechanism we are fearing is the dephasing of this amplitude of these superpositions, okay? That this plus may go into an plus e to the I phi, and then the superposition is a little bit messed up, but the amplitudes cannot decay because we are anyways in the ground state, and the lifetime is infinite. Okay, so this is how we address this with laser beams, but I can show all the details. Sorry, you should visit me one day and then I show you all the lasers, I tell you. So everybody who is interested just books a travel to Mainz and visits me in the lab. And
after the end of the corona,
show this around. Yeah, exactly. When we are no longer in the corona condition.
Let me ask a last question. I see is can you get rid of multiple errors with the post-processing in a quantum computation?
So we can get rid of multiple errors. That is, we need codes which are at higher distance. Okay, and for this we need even more qubits. This is, of course, you know, if you have 100 qubits and then you say that would be already a fantastic quantum processor, and then you take 10 qubits each for implementing one mathematical qubit. This is already a lot, and then so to start error correction, you need to have lots of qubits which are working pretty nicely. That is why people are interested in quantum error correction only from the fundamental side of view at the moment. That is why we are still following this noisy intermediate scale processors where we say, okay, we know it's not perfect, but we want to make it somehow to the point where we can show something that a classic computer cannot do. And when we reach this, then we hope that now at that moment, everybody will be happy. And then we have a lot of time and a lot of resources to build the quantum error correction really on large systems. But as I told you, you need 28 qubits or so to correct a second error. And this goes on. And this is already a very efficient code. So there are codes of distance 1, codes of distance 2, and so on. And I think Simone is much better in answering this question as compared to me, because this is still a lot of theory, and we are not there to do this. We are battling with our few qubits, and our error code with our 7 data qubits is already this is hard enough for us. Okay. But you can find recipes, but they are at the moment pretty unrealistic to implement.
Yeah, so thank you very much. I think I don't see any more questions. Thank you very much, both for the lecture and for the very detailed reply to all the questions that have been posed. Thank you again. And
Yeah, I thank you very much and goodbye.
bye.
Thank you very much, Ferdinand.